Hi students, Professor Nugent here. In this video we are going to talk about multicollinearity. Multicollinearity is almost as fun to say as heteroscedasticity, but is much more of a problem. Perfect multicollinearity is when one of the regressors is an exact linear function of the other regressors. Let's look at some examples. We have one from before where we accidentally include one of our variables in the regression twice, and in that example we saw that Stata is going to drop that variable like it's hot. A second example may be where two variables are copies of each other but have different names. So if we regress test score on a constant d and b, where di is equal to 1 if the student to teacher ratio is less than or equal to 20 and 0 otherwise, and a variable bi which is equal to 1 if the student to teacher ratio is greater than 20 and equal to 0 otherwise. This means that bi is equal to 1 minus di, so they're going to move in lockstep with each other. They have a perfect linear relationship, a one-to-one relationship. And there is perfect multicollinearity between these two variables if you include both d and b in the regression for test score. We can ask, would there be perfect multicollinearity if the intercept were excluded from this regression of test score on D and B? And that the answer is that no, there would not be perfect multicollinearity. This example is a special case of using one of these variables as the constant regressor to represent the intercept. So perfect multicollinearity, again, this is either where you have a variable included twice in the regression, or you have two variables where one mirrors the other, but maybe they have different names. And in that case, the second case, they are moving in lockstep with each other, one-to-one, whether they are dummy variables or not dummy variables. Now, when we are working with dummy variables, things can get a little bit more complicated, especially when we have multiple dummy variables to represent a group, and we're thinking about representing a group's categories or characteristics, so we have many different characteristics. Suppose that there are multiple categories and every observation falls in one and only one category, such as freshmen, sophomores, juniors, seniors, and other. If you write a dummy variable for all of these categories, such as f equals 1 if freshmen and 0 otherwise, so equals sophomores, so equals 1 if sophomores and 0 otherwise, j equals 1 if juniors and 0 otherwise, and se equals 1 if seniors, 0 otherwise, and ot equals 1 if other and 0 otherwise. If you include all of these dummy variables, fr, so, j, se, and o, then you will have perfect multicollinearity, and this is called the dummy variable trap. Now, why is this going on? Well, let's make sure we're drawing. I think we're drawing. Alright. You would have fi plus soi plus ji plus SEI plus OI equal to 1 for all I. Okay, and so you would have perfect multicollinearity with the constant regressor with the intercept, because this set of dummy variables is always going to be equal to 1. There is no variation across the observations, across I. There's the sum of these variables will be equal to 1 for all I. So what do we need to do? Well, there is a very easy solution, that is to omit one of the groups. We can also omit the intercept. There are different implications here. The easiest thing to do is to omit one of the groups. And when you omit one of the groups, then what you have for the coefficient on the dummy variable is the relative difference between the, let's say, the freshman group and the omitted group. So if we omit senior and we look at the beta that is on freshman on Fi, we have omitted senior, then beta F on freshman is going to give us the effect of freshman on the outcome variable, its difference between Fi and senior. Alright, so we have the relative difference between freshman and senior. Taking this one step further, perfect multicollinearity usually reflects a mistake in the definitions of the regressors or an oddity in the data. If you have perfect multicollinearity, your statistical software package will let you know, either by crashing, giving an error message, or dropping one of the variables like they are hot. The solution to perfect multicollinearity is to modify your list of regressors so that you no longer have multicollinearity. So this is a big problem, but it is pretty easy to fix. Now what about imperfect multicollinearity? These things are quite different despite similarity in the names. Imperfect and perfect multicollinearity are quite different despite the similarity of the names. Imperfect multicollinearity occurs when two or more regressors are very highly correlated. Now, why the term multicollinearity? If two regressors are very highly correlated, then their scatter plot will pretty much look like a straight line. In other words, they are collinear. But unless their correlation is exactly plus or minus 1, that collinearity is imperfect. What might be an example of this? Well, an example might be the relationship between the federal funds rate and the term spread. So if we looked at the federal funds rate on the y-axis and the term spread on the x-axis. Recall that the federal funds rate, this is the policy interest rate set by the Federal Reserve. The term spread is the difference between short-term interest rates and long-term interest rates. Basically, what you're going to see is that the term spread is going to be low when the federal funds rate is low, and the term spread is going to be higher when the federal funds rate is higher. So, and the variation between these things is going to be quite tight. But you may see imperfection because the term spread is not going to increase 1 for 1 with the federal funds rate, because the term spread is not only determined by the short-term interest rates, but it's also determined by the long-term interest rates. So you have variables that are highly correlated, but imperfectly so. If we have two variables in our regression that are demonstrating imperfect multicollinearity, that implies that one or more of the regression coefficients will be imprecisely estimated. Here's the idea. The coefficient on x1, let's say x1 is the federal funds rate, the coefficient on the federal funds rate is the effect of the federal funds rate holding the term spread constant. But if the federal funds rate and the term spread are highly correlated, which they are, there's very little variation in the federal funds rate once the term spread is held constant. So the data does not contain much information about what happens when x1 changes, but x2 does not. If so, if we have these two variables in the regression, both x1 and x2, what we're going to see is that the variance of the OLS estimator and the coefficient on x1 is going to be large. So this is the result of imperfect multicollinearity. This is what happens, okay? And correctly, imperfect multicollinearity results in large standard errors for one or more of the OLS coefficients. The math that is in the appendix, and a bit outside the scope of this course, but it's important to know that if you have two variables in your regression, such as a short-term interest rate, like the federal funds rate, and the term spread, it's hard to look at the effect of the variation in one variable holding the variation in the other variable constant when the two variables are highly collinear. And so we're not going to be able to estimate one of the coefficients very precisely. Since we lose that precision in estimating that coefficient, we have a large standard error. Okay, so that is the outcome. We get a large standard error because of the imprecision in estimating one of the coefficients.